Hello, my name is Justin Oka. I am currently a third year student at the University of Texas at Austin. I am pursuing a major in mechanical engineering and a minor in computer science. My project title for the summer is The Modeling of Ductile Failure Using Machine Learning. The mentors I have been working with are Amin Benzerga and Aitor Cruzado. The grad students I am working with are Vigneshwaran Radhakrishnan and Francisco Medrano. Lastly, the ORU student I am working with is Osvaldo Quintero. Before we go any further, I want to note that this work was supported by the Department of Energy, National Nuclear Security Administration, under award number DE-NA-0003857. It's important to talk about realizations and how they relate to the project. Displayed below, you can see some sample realizations that were generated by one of my colleagues. As you can see, they can vary widely in appearance. In the figures, the small x's represent void centers, and how they are spread out across the realization is the void distribution. Realizations can vary between ordered, random, and cluster distributions depending on different parameters we pass into them. Furthermore, ordered and random are generally well understood compared to cluster distributions. Given that brief slide about void distribution, let's talk about the motivation and goals for this project. We really would like to understand the effects of void distribution on ductile failure. Because of this, we are using machine learning to help model the ductile failure of a material with different initial void distributions. We will first receive a large number of realizations with different void distributions, varying between ordered, random, and clustered, and simulate increasing strain on the realizations. All this data is coming from simulators created by other colleagues working on the project. These simulations are very time-consuming and could take hours or days to fully complete. Because of this, we are creating a neural network to remove redundant realizations and finish with only 1% of the initial realizations. This would greatly reduce the time needed to run. Furthermore, these remaining realizations would be statistically representative of the original set. Before any of this begins, the neural network must first be trained. It will be trained similar to that of a game with rules and an end goal. The rules will be set at the very beginning and will not change, and the end goal is to finish the simulations with a minimum number of remaining realizations. For example, let's say we start off with 1,000 realizations, and our minimum is 10%. A victory for the game will be to finish with at most 100 left. Anything more would be considered a loss. So, if we finish the game with 200 left, that's considered a loss. However, if we finish with 50 left, that's considered a victory. Of course, this is a simplified explanation, but this is the basic principle that the neural network will be using to determine whether a game is won or lost. The neural network improves over time and will learn the best way to achieve a victory, and it will be able to consistently reach the minimum threshold and produce remaining realizations that are statistically representative. We've already talked quite a bit about what a victory looks like. We just want to reach a minimum threshold of remaining realizations. But how do we turn the number of realizations into a game? Well, let's talk about the game mechanics. Let's start with a board. You're going to have a two-dimensional board that functions similar to a histogram. Right here we can see our board, where the x and y axes specify certain criteria. The number in each cell represents the number of realizations that fit that bin criteria. Next, let's talk about a move. To move is to either remove or keep a realization. Here, a possible move would be to remove a value from the center position, and we can see here that the center position went from 2 to 1 when compared to the previous board. Another valid move would be just to leave the board unchanged. Lastly, after each move, we refill the board with new data. This new data is from the void centers changing because of the increasing strain. You'll notice that in this third board that the numbers have switched positions because the realizations have new data points that put them in different spots. Let's delve into what the game is looking at right now. We can use data from the Lambda simulator to help visualize the board. The Lambda simulator is a script that simulates the increasing strain on the realizations, and it tells us how the realizations are changing over time. In the beginning, we decided on using lambda and delta lambda values from the simulator as criteria for the board. Although this is not the case right now, this is still a good visual aid for understanding. Looking at the picture on the right, each table represents how the realizations are evolving over time. You can see iteration 1, 2, 3. The values on each axis describe a range that either lambda or delta lambda is contained in. You can think of each spot as bins of a histogram, and the value as the height of the histogram column. Each cell on the table represents a spot on the board, while the values represent how many realizations are contained in each bin. So, very similar to a 2D histogram. In order for our game to work, we are basing it off an AlphaZero program that has already been developed for the game Connect 4. This program creates two neural networks and has them play against each other over time. After many iterations, both improve enough to play Connect 4 at a very high level. AlphaZero is special because it requires zero human input and has an elegant algorithm. Furthermore, it makes use of two very important aspects. First, the Monte Carlo search tree. This is a search algorithm that can store and explore different possibilities. For example, it can store different moves of a board game and look ahead at future board states. The second is the convolutional neural network. This is a type of neural network that senses patterns within two-dimensional data, like pictures or game boards. Right now, the AlphaZero AI is currently running and just needs to be modified to fit what we want. We will be taking different scripts and rewriting them to fit the game that I've described. This is a daunting task because Connect 4 is vastly different from our game, meaning that many of the scripts will have to be altered for our game to work properly. As I mentioned before, AlphaZero has multiple scripts that require significant change. This includes games.py, which controls the rules and the operations of the game, agent.py, which calls the Monte Carlo tree search and simulates moves, and funcs.py, which calls the agent class. Furthermore, we have three main steps for the game: filling the board, which uses MV clusters and delta lambda values as criteria, simulating the actions, which fills the Monte Carlo tree search with different board states, and taking the actions, so a move is selected from the Monte Carlo tree search to be taken. In the code we have currently running, I've modified it to print out board states when filling with new values, when simulating different moves, and when taking a final action. As of right now, we can see the board being filled with data, as in we can see the numbers pop up in the board visualization tool we have. We can see the Monte Carlo tree search being filled with leaf nodes. We can see various moves being simulated, as in we can see the Monte Carlo tree search looking ahead at different board possibilities. And we can see various moves being taken, meaning that we can see a move being chosen from the simulated possibilities. In the future, though, we have a couple things to work on. We definitely have to debug the program so that the game runs to completion. Right now, there are numerous errors and bugs because we have modified the original AlphaZero code so much. Also, we need to determine whether the current Monte Carlo tree search and convolutional neural network fit our goals. Right now, the MCTS and CNN are designed to run for Connect 4, and we don't know yet if they are completely transferable to our project. I want to conclude by saying that this program was incredible fun and that I learned so much in the past 2 months. Thank you to my mentors Amin Benzerga and Aitor Cruzado, who have helped me every step of the way, and to my colleagues who I've been working alongside with this entire summer. Thank you to those leading the ORU program. This wouldn't be possible without all of you either. And to all of those listening, thank you for your time. It's been a pleasure.